and today we are going to cover chapter 3. Let's see here. So chapter 3, and we're going to talk about what's called linear programming. And what this is going to be related to is basically graphing straight lines and finding the region above or below these lines that satisfy certain conditions. And we're going to take a graphical method to doing these. And it's going to be very straightforward. I'm sure nothing that, well, probably most of you have probably seen this before. So we're going to go this step by step. So this should be a pretty straightforward video. Probably shouldn't take very long at all. And we'll go from there. So section 1 is called linear inequalities. Okay, graphing linear inequalities. And that's where we're going to start. Okay, so here's what we're going to be looking at. Okay, so we're going to look at inequalities, and we can have inequalities that have many different forms. Okay, these are a couple of ones, and we're only going to be dealing with, at this point, two variables. So we could have something that looks like this, where we have a system of and x and y that is less than a constant, less than or equal to a constant. We could have something that looks like this, a linear expression that is less than a constant, or we can have greater than or equal to or greater than. Okay, and again, we're assuming that a and b are not both 0, and a, b, and c are real numbers. Okay, so if we look at this line, so we're given, let's say, an inequality. Okay, the first thing we're going to do is treat it like it was an equation. So this goes back to what we already discussed in previous chapter. So we're just going to graph the line, right? We're going to graph the line that represents the border of the shaded region, which is just the straight line, the equal part. Okay. Now in this case here, we're dealing with it could be less than or equal to, greater than or equal to, less than or greater than. Now because it's an equal sign, so the inequalities that include an equal sign, like less than or equal to or greater than or equal to, we want to draw this as a straight line. And it's going to be a solid line. So this is going to be one solid line. That's going to be if the inequality has the equal sign involved in it. Now, if it's greater than, so once you plot the line, then it's very easy. If it's greater than, if greater than is included, it means everything above the line satisfies the inequality. If it's less than, then everything below the line. And the easiest way to see that is if you look, see how it's in this form? Well, if you want to know whether it's above or below the line, all you have to do is put this into slope-intercept form, because then you know it's going to be y is greater than or equal to, or it'll say y is less than or equal to, or it'll say y is greater than or y is less than. As soon as you know that, you'll know whether you're above or below the line, because if it's y is greater than whatever this is, then you're above the line. If y is less than, then you're, oh, hold on, I'm sorry, I misspoke. Above the line, I think I misspoke there. So if it's greater than, y means that you're above the line, less than means that you're below the line. So in this case here, we have 2x minus 3y is less than 12. And so in this case, when we solve this, what do we get? We get what? We get negative 3y is less than negative 2x plus 12. But then when you divide by the -3, it flips the inequality. See, and that's where you can kind of get the wrong answer. If you just look at this form and you think, oh, you plot the line, oh, it's less than, oh, okay, it must be down here. That's not true. That's not always true. Okay, so the best way to do this is solve it for the slope-intercept form. Okay, or if you put it in this form, if you leave it in this form and you graph it, let's say you take a couple of points, right? You set this equal to 0, and you solve for y, and you get this point. And then you put this for 0, and you solve for x, and you get this point, and you graph the line. Well, what you could do is use what's called a test point. And so in this case here, they're using the origin as a test point. Okay, 0, 0 is always an easy one to use. Now, if you use a test point and you get a result that is a true statement, then you know that that point lies in the region where all of the points satisfy the inequality. Okay, so there's a property that says that, hey, if one point on one side of the line satisfies the inequality, then all of the points on that side of the line also satisfy the inequality. Okay, now if you have one side of the line where one point includes, or excuse me, satisfies the inequality, well, then that means the other side of the line cannot satisfy the inequality, because it's either got to be one side of the line or the other side of the line. It can't be both. Okay, so you don't have to use a test point over here if you use one over here, because if it satisfies the inequality over here, then all these points will not. If it does not satisfy over on this side, then all of the points over here will. Okay, so you really only have to use one test point. Okay, and the origin is always a great one to do, because the origin will usually be on one side or the other side. The only time you won't be able to use the origin is if the line goes right through the origin. In that case, you'll have to use some other point. Okay, so now here's another example. Okay, so notice we have this, right? And so if we solve this, let's do this real quick. Okay, so if you solve this, what are we going to get? We're going to get y. And notice this negative sign here. We're going to end up dividing by a -4, right? So that means we're going to have to flip this sign. So this is the result is going to be less than. Okay, so we're going to subtract x from both sides. So we're going to get -x. Okay, and then we're going to divide by -4. So that's going to make this a positive, and it's going to be x over 4. And this is going to be what? -1. Okay, so what we're going to end up doing is we're going to get y is less than 1/4 x minus 1. And so this is the line. Now, since it's in y-intercept form now we know that all of the values are going to be below the line. Okay, all the solution values are going to be below the line. So any point that's below the line will satisfy this inequality. Okay, so again, you can use your test point. If you use 0 here, you get 0 is less than what? -1. Is that true? No, of course not. 0 is not less than -1. It's greater than. So that means this is not the side that's the set of solutions. It's going to be this side. Now notice here we use a dotted line for the border. Well, that's the line. So if you solve y equals 1/4 x minus 1, you're going to get the line. But why is it dotted? Because it's a less than. It does not include the equal sign. So if it's a strict inequality like less than or greater than, then the border, which is represented by the line, is going to be dotted. Okay? So let's look at this. Oh, this didn't work out very well. Okay, so anyway, let's graph this inequality. Well, the first thing we're going to do is we're going to um, look at what it looks like as far as the boundary line. Okay, so the boundary line is going to be equal to, right? So we use the equation to find the boundary here. Okay, the line that represents the boundary, and we're going to plot this thing. Now, again, the way I would plot this is write in slope-intercept form, because then you can plot it easily. And so in this case, you're going to get y is equal to what? It's going to be negative 3/2 plus 9. Okay, so then you can graph the thing easily on the graph. Okay, now since the points on this line do satisfy this equation, then you're going to have a solid line because of the equals, right? So we're going to have a solid line that represents the borderline. And then to decide whether to shade the region above or below, you can use a test point. So again, if you just plot some points, and in fact, in this case here, you can use the slope-intercept method. So if you don't want to solve for the line, that's fine. All you have to do is plug in 0 for x, solve for y. So in this case here, if you plug in 0 for x, you get y is equal to 9. So you get the intercept, um, the y-intercept of 0, 9. And if you want to make the y 0, then you get x is equal to what? 6. And so you get the x-intercept 6, 0. And so when you plot those 2 points, then you get a line, right? Okay, so in this case, it'll be a solid line. Well, then this is where your test point comes in. You choose the origin, right? Because the origin is either going to be on one side or the other side for the most case. Okay, here you get 0, 0, so you get 0 equals 18, which is false, right? Or excuse me, I'm sorry. Now I was looking at the equal sign. In this case, 0 is less than or equal to 18. So in this case, this is a true statement. So the origin lies in the region that contains all the solutions to the inequality. Okay, so that tells you which region to shade. Okay, and so now this is the region. So here's the intercepts, right? You connect them with a straight line, which is solid, and then the origin is made a true statement. So everything on this side. So we shade everything on the side of the line. So there's two different ways to do these. You can solve the inequality and put it in the slope-intercept form, okay? And then you plot the line, and then you know instantly whether you're going to plot below the line or above the line, okay? Or you can leave it in this form, standard form, and use the intercept method to plot the y, x, and y intercepts, and then use a test point and to see if the test point gives a true statement or a false statement. And if it gives a true statement, you know that everything on that side of the line is a solution. If it gives you a false statement, then you know everything on the other side of the line is a solution to the inequality. Okay? So now half planes. Okay, so what do we mean by half plane? Very simple. The half plane is one side of the line. So every line goes on for infinity. So we just represent a line with these arrows, right? Which represents that, hey, this continues on to infinity, okay? So that means it splits the plane into two halves, which we call half planes. So one side we would call half plane P, let's say, and we can use whatever letter we want. And the other side we could call the half plane Q, okay? And then this R here would be, let's say, the line, the boundary line, okay? So we usually use lowercase letters to represent lines, okay, and then capital letters to represent half planes or points and things like that. So now on the calculator, it is very easy to graph half planes because you can use a symbol And this is where you go to the y equals, and to the left of each equation you can change um, whether you want to shade above or shade below. So again, I'm not going to show you that here, but ask me in class and I will make sure that I show you on the calculator how to do this. But it's very easy. Also in the textbook, it shows you step by step how to do it in the textbook. So um, definitely read the textbook. So it shows you how to do um, this type of graphing on your calculator. Okay, now graphing a linear inequality. So here are the steps. Okay, so step number one, draw the graph of the boundary line. Make the line solid if the inequality involves these two. Okay, so if it has the equal sign with it, it'll be solid. Make a dashed line if it's a strict inequality. Okay, then two, decide which half plane to shade. Use either of the following methods. Solve for the inequality for y. Shade the region above the line for the inequality if it's of the form greater than or equal to. Okay. Shade below the line if the inequality is less than or less than or equal to. Okay. B is choose any point not on the line as a test point. Shade the half plane that includes the test point if the test point satisfies the original inequality. Okay? Otherwise, you're going to shade the other side. Okay, and that's really the easiest part. It's either this one or this one. Okay, and both of them are just as easy. Okay, what about systems of inequalities? So what if you have two or more inequalities and you want to find the region that satisfies all of the inequalities? Okay, so this is where we're going to have multiple shaded regions. Okay, and you could either do this on the calculator or by hand. Now, if you use the calculator, you have to solve each inequality in for y. So you have to have it in the slope-intercept form because you're going to have to plot it. That's the only way the calculator will allow you to plot the lines, right? So once you plot the lines, and then also you can then change the shading once you use a test point. Okay. Okay. Oh, by the way, you could also get the calculator to shade in these regions because you can change the equal sign um, to less than or equal to or things like that. But again, ask me about this and we'll go over this in class. But again, most of this is we're going to be doing it in by hand, but also practice using the calculator because this is going to make things easier on the exam in a lot of cases. But again, I may ask you to shade something in, so you'll have to do it by hand. So again, practice both of these. Okay, let me put this back to pointer. Okay, so here's what we're doing. So here's one line. So this is actually y equals 1/2 x. Okay, and then this one here is the line what? Y equals negative 3x plus 12. And again, both of these are strict inequalities. So we plot the boundary lines, right? For this one, plot the boundary line for this one. And then now notice that this goes right through the origin. So in this case, we're not going to be able to use the origin as a test point. Okay, but here's the way it works. Okay, how do we solve these? Well, it's very similar to what we did before. Okay, so you're going to use a test point. But look, we need to find the region where both of these are satisfied. So in this case, instead of having one test point, we're going to have possibly 4 test points because we have to find the region that satisfies both of them. So we're going to have to find a test point in this region, use a test point in this region, a test point in this region, and a test point in this region, and find which one of those points gives a true statement for both of these. Okay? And so that will tell us, hey, if now again, we could have multiple solutions, but again, in this case, we're either going to get one of these few um, inequalities. Okay, so we're going to, in this case, we're going to have multiple test points to use. Okay, but if we solve this in terms of the y-intercept form, then we know, hey, if it's above this line and below this line, right? So in this case, let's say it's above this line and below this line. Well, it automatically tells us which region it is, okay? But if you don't put it in the y-intercept form, then you have to use test points, and you're going to have to use a point in each one of these, or until you find the one that works, okay? So just be aware of that. So let's look at this one. So it says find the feasible region for the system. So we want to find the region that satisfies this system of inequalities. So in other words, we want to find the region that makes both of these true. Okay. So again, we're going to have to plot both of the lines that represent the boundary lines, and then find which region satisfies both of them. Okay. So the boundary line here is going to be this, right? So we're going to use the equals, right? Since the points on this line do satisfy this inequality, the line is drawn solid, right? Because it has an equal sign in here. To decide whether to shade the region above the line or below the line, we will choose the test point. Okay, and again, we can use 0, 0. Okay, and in this case, 0, 0 gives us a false statement, and so 0 is not included in the region. So we're going to shade the region on the other side of the line. For the second inequality, we're going to use this boundary. Okay. Now, since this also satisfies the line because it has equals, it's going to be another solid line. Okay. And then to decide whether to shade above or below the line, we're going to choose another test point. Now, we're not going to use the origin because it goes through the origin. Okay. So we want to use some other point. So another good point to use is 1, 0. Right? We could use 0, 1 as well, but 1, 0. Okay. We replace x with 1, y with 0, and what do we get? We get 1 is greater than 0, which is a true statement. So we know that this point lies in the region that satisfies the inequality. Okay, so we're going to shade everything on that side of the line. Okay, so the half plane that contains 1, 0 is the region we're going to shade. Okay, and when we do that, we get this shaded region. Okay, now again, you could have just solved both of these in y-intercept form and then just say, okay, well, what region satisfies both of those? So you don't have to use test points if you solve these in the y-intercept form. Okay, if you leave it in this form here, then you'll have to graph it using the intercept method and then use test points. So now let's look at this one. So it says graph these two. So now this case here, we've got this line, right? So this is already in y-intercept form, slope-intercept form rather. Okay, so we can use this, and we know that, hey, we're going to plot the line, and we know that we're going to be below the line. It's going to be a solid line, and then we're going to shade everything below the line. Okay, but here we have vertical lines. Okay, and so what this is saying is that, hey, we're going to have a vertical line at 1 and another vertical line at -2, and we're going to shade everything in between those two vertical lines. Okay, so this is actually an easy one to kind of think about because we're going to have two lines, x equals 1, which we know is a vertical line, and we have x equals -2, which is another vertical line. And so this is going to be easy to visualize. Okay, so when you plot these, this is actually what you're going to get. So you plot the first line. So again, here's the boundary line for this line. And then here are the two vertical lines, x equals 1 and x equals -2. And so we know we're going to be below this solid line. So we know we're below this line, but we also have to be in between 1 and -2 on the x-axis. So we know that our boundary line, our region is going to be everything below this line, but also between these two lines. And so this is where we get the region. And of course, if you put the origin in there, you get that 0 is indeed between these two, and we get 0 is less than 8, less than or equal to 8, which is true. So again, you could use the test points, but if you just understand how to um, think about what's going on with these lines, especially if it's in slope-intercept form, it's very straightforward. Okay, what about this one? So here we have these four. Okay, so now it's a little bit different, but again, we can still tackle this. But notice that this is a vertical line. So we're saying, hey, we're only interested in all of the points that are above the line y equals 0. So we got the vertical line y equals 0 is a boundary line. And now we're only interested in the points that are greater than 0, x equals 0, right? So greater than that. So that means this is going to be everything to the right of the horizontal line. Excuse me, I mean the vertical line. X equals 0. Okay, so these are these two boundaries. And then of course with these two we could solve for y, excuse me, and put it in y slope-intercept form, and then we could easily find it. Or again, we could use the test points. Okay, we could use the intercept method and plot these lines, and then use test points. Okay, either way, you're looking for the region that satisfies all four of these conditions. Okay, so now in this case here, let's find out, just so you know. I'll do it with the slope-intercept form, and let's see what we get. So this one here, we get what? We get y is greater than or equal to y, because we're going to be dividing by a negative number, so this means that we're going to have to flip the sign. And so in this case, we get 2/5, so it'll be okay. So we're going to get 2/5 x, okay, and then we're going to get minus 2, okay, and then this one here is going to be y is less than or equal to, okay, and I leave the inequality the same because I'm eventually going to be dividing by a positive number, so it's going to stay the same, and then I'm going to get negative 1/2 x, okay, and I'm going to get plus 4. Okay, so I know immediately, I know I'm going to have all of the values above this line, and here I want all the values below this line. And then I want everything above this line and everything above or to the right of this line and above this line. Okay, so the only one that we don't talk about above and below are the vertical lines. We always, with the vertical lines, it's either going to be to the left or the right, and that should make sense because remember the x-axis, negative numbers go to the left, positive numbers go to the right. So it's always less than is going to the left, greater than is going to the right. Okay. So, but if we put all of these together, we get this. So again, we plot these lines. So here's this line, okay, and here's this line. So in this case here, we're greater than this line. So we're greater than this line. So we're above this line, but below this line. Okay, so we would be in between these two lines, but then we want to be above the x-axis and we want to be to the left of the y-axis, or excuse me, to the right of the y-axis. So here's the boundary for this one, okay, the y-axis, And then the boundary for this one is the x-axis, so we want to be above the x-axis, but to the right of the y-axis. We want to be below this line, but also above this line. So this region is going to be everything that's in between all four lines. Okay, and so again, here we would not use the origin because the origin is actually on the line, so we wouldn't use the origin, but we would use, let's say, 1, 1. We could use the point 1, 1. And we could plug in 1, 1 for all these. So in this case here, we would get 2 minus 5, which is a negative number. So we know a negative number is less than or equal to 10. Here we would get 3. We know 3 is less than or equal to 8. And here we would also get 1. 1 is definitely greater than or equal to 0, and 1 is definitely greater than or equal to 0. So 1, 1 works. So that means everything in this side of all the lines would work. Okay, so again, you could use just what I did was using the slope-intercept form, and then just look at the inequalities, or you could just use the slope method, or excuse me, the intercept method to graph the lines and then use test points. Okay, or in this case, one test point worked. Okay. And the reason why we only use one test point is because, remember, we're looking for one point that will satisfy all of these. Okay, so you look at the bounded region. Okay, and the easiest way to do it is if you take the bounded region, the region that's bounded by all of them, that's in between all of them, then if the point works, then you know everything inside that region satisfies all three equations. If the point doesn't work, then all bets are off, because that means that one or more of the equations is not going to be satisfied. Okay, let's look at this one. So here we have a system of three equations, x and y. And so again, let's go through the steps. We're going to graph each of the lines. Then we're going to figure out what region satisfies each of the lines, and then we're going to find the overlap, right? Where the regions overlap. So now in this case here, look at this. This region, so A, so this region here, so here's this line, and so this shaded region represents all of the points that satisfy this linear inequality, this inequality here. And then we look at this line here, y equals 1, so that's the vertical line, or excuse me, the horizontal line. And so we want everything below this line. So that means this region here, okay? Okay, so we're talking about this region here. And then the blue line here, which represents this inequality, is everything that's above here. Okay, so it's going to be this region. Notice that there is no region where all three overlap. Here we have these two overlap, right? And then over here we have an overlap here, but it's between these two lines. And then we have this overlap, but there's no region where all three overlap. In fact, the only region where all three overlap would be if it was inside this region. Okay? So in this case, there is no solution. Okay? So again, if you look at the bounded region, so this, in this case, it's this triangle inside. This is the region where all three lines create a boundary, right? So if the point in here satisfies all three, then this is the region that would be the solution. But if you look at the shaded regions, there is no shaded region. I mean, there's nothing shaded in here. So this tells us that there is no solution to the system of inequalities. Okay, so again, you could use test points to test that out, right? So you look at the lines and you see where the boundary is, okay, and then you use the inequalities to figure out what shaded region it is, or you could use test points to find out whether this region satisfies or not. If it doesn't, then that means you have to be outside and there's not going to be any solution to it. Okay, so let's use a manufacturing example here. Okay, so it says, Happy Ice Cream Cone Company makes cake cones and sugar cones, both of which must be processed in the mixing department and the baking department. So manufacturing one batch of cake cones requires 1 hour in the mixing department, 2 hours in the baking department. And producing one batch of sugar cones requires 2 hours in the mixing department and 1 hour in the baking department. It says each department can operate at most for 12 hours per day. That's the restriction. Okay, so 12 hours a day is it. It has to be less than or equal to 12 hours. Okay. A says write a system of inequalities that expresses these restrictions. Okay, the restrictions are that hey, cake cones, 1 hour takes 1 hour in the mixing department, 2 hours in baking. Okay, to make one batch of sugar cones, it's 2 hours in mixing, 1 hour in baking. Okay, so those are also restrictions, and then of course each department is only going to be open for 12 hours. Okay, so A, we want to write the system of inequalities that expresses the restrictions. B, graph the feasible region. And C, using B, find out if it's possible to either make 3 batches of cake cones and 2 batches of sugar cones in one day, and also check to see if 4 batches of cake cones and 6 batches of sugar cones can be manufactured in one day. So basically, these are going to be our test points. So A, write the system of equations. So in this type of application problem, we want to set up a table, right? So the easiest way is set up a table. We have what? We have number of hours in each department, okay? And then we have the type of cone that's being made, okay? And so X represents the batches, okay, of cake and sugar. So Y represents the sugar cones, okay? This is the number of units made, okay? In other words, batches. So the number of units made is X cake cones, Y sugar cones. The hours in mixing. So for one batch, it's going to be 1 hour. For sugar cones, it's going to be 2 hours. And then for hours in baking department, it's going to be the other way, 2 and 1. And so this total number of hours has to be less than or equal to 12. And this total number of hours has to be less than or equal to 12. So it's going to be 2 hours for every batch. So it's going to be 2x. So our system of equations is going to be here for the cake cones. It's going to be 1 hour, right? So how many batches can we make in the mixing department? Well, it's going to be 1 hour for every batch of cake plus 2 hours for every batch of sugar cones. And so this sum cannot be bigger than 12. And then if we take the baking department, we know 2 hours for every batch of cake cones plus 1 hour for every batch of sugar cones. So this total number of hours cannot be more than 12. Okay, and that becomes our system of two equations with two unknowns. Okay, so our system of equations will actually look like this, just so you know. So our system of equations, let me write this down. Okay, so it's going to be x plus 2y is less than or equal to 12. And this is going to be 2x plus y is less than or equal to 12. And by the way, just so you know, you could set this up as a matrix equation. So you could have 1, 2, 2, 1 times what? X and Y right, is equal to 12, 12, right? So we have 12. This is not going to look pretty. 12, 12. And so this is how we would represent this system of equations as a matrix equation. And then again, all we'd have to do is find the inverse, and we get xy is equal to the inverse times the 12, 12 matrix. So again, you don't have to do that way. I'm just showing you that, but this would also be a way of solving this. And again, we probably will get into this a little later. But again, we're just going to use what we know for right now. So we're going to plot both of these, and then we find the region that satisfies both inequalities. Okay, so here's what we did. So here's your graph, right? So this part B, so we graphed the line here, and we graphed the line here, and now we've got 4 regions. We got this one, this one, this one, and this one. So we want to find the region that satisfies all of these. Well, obviously, where do these come from? Well, we definitely need the number of batches to be greater than or equal to 0, and the number of batches of each of these be greater than or equal to 0. So these are some unmentioned restrictions that, again, you don't want to ignore, because, again, this has to make sense in the real world. So we know that we can't have negative batches. So we know we're going to be above the x-axis and to the right of the y-axis. So we know that the region that we're interested that's bounded by all of these restrictions is this region here. Well, guess what? This region is our solution region. Okay? Now notice we didn't have to do any test points, right? Because we want the region that's less than, that's bounded by all of these regions. The region that is bounded by all, or rather, restrictions. So the region that is bounded by all of the restrictions is the solution region. Okay? So, and you see that by just pick a point in here. Okay, and you'll know that a point anywhere in this region will satisfy all of these restrictions. So notice that 3 hours of x, right? So 3 batches of x and 2 batches of y will satisfy all of them. But if I want to do 4 batches of cake cones and 6 batches of sugar cones, well, that I won't be able to do that, right? So immediately I know what can I do, what can I manufacture, what can I not manufacture, what's possible, what's not possible in this system. Okay, so that ends this lecture video. So next time we're going to talk about solving linear programming problems graphically. Okay, so we're going to talk more about this and take it one step further. So until next time, make sure you please work through these examples and the other examples in the textbook. Okay, make sure you're writing down all of your problems and all of the questions you have. Bring them to class, because we're going to work through those. So make sure that you have things to work on, because the first thing I'm going to do is ask, hey, what questions do you guys have? So make sure you're prepared before class. Make sure you have all your questions. Make sure you have anything from the homework, any problems that you're working through that you got stuck on, because those are what we want to tackle, and then go on and actually just be prepared to practice in class. Other than that, until next time, have a great day, and I'll talk to you later. Bye-bye.